In this video, we're going to talk about the connection between uniform convergence and continuity. So recall the definition of uniform convergence of a sequence of functions. So suppose that f1, f2, f3, ... is a sequence of functions that all have the same domain and codomain from one metric space to another. So a sequence of functions from the metric space E to the metric space E prime. Then we say that the sequence converges well, first it needs to converge. So suppose that this sequence converges. That's maybe what I should have said first, before defining the uniform convergence. So suppose that f1, f2, f3, that sequence converges to some function f. Okay. Then we say that the convergence is uniform, so we say that the sequence f1, f2, f3, ... converges to f uniformly if for every epsilon greater than 0 there exists some capital N, some positive integer capital N, such that for all integers little n greater than capital N, and for all p in E, the distance between f of p and fn of p is less than epsilon. So let's say that you had functions from reals to the real numbers. So E and E prime are both R, and we're graphing these functions. So you have that limit function f, and then what's going on is you have all these fn's, and what's going on is that for every epsilon, so imagine this epsilon band, it's just shifted up epsilon and then shifted down epsilon. So this distance is epsilon, this distance is epsilon. It's saying that, so you have all these fn's, eventually past some capital N, all the fn's stay within this epsilon band. Right? So all your fn's for n greater than some capital N will lie in this epsilon band. And so what's going on is that intuitively what we're saying is that f and fn are never more than epsilon greater than each other. Right? There's no point p for which f of p and fn of p are more than epsilon away from each other. Okay. So we can think of this as saying that for all epsilon there exists a capital N, such that for all little n, the distance between f and f sub n is less than epsilon. Like the biggest possible distances between the f of p and fn of p. That's what we mean by the quote-unquote distance between f and fn is less than epsilon. Okay, so that's just a review of the definition of uniform convergence. And then the theorem that we're going to prove says that if f1, f2, f3, dot, dot, dot is a sequence of continuous functions that converges, so the sequence converges uniformly to the limit function f, then f must be continuous. So what this is essentially saying is that your limit must be continuous, right? If you think of these fn's as approximating the function f, if your limit function can be approximated arbitrarily close by continuous functions for every epsilon, then the limit function f must also be continuous. Now the proof that's presented in a lot of linear algebra, in a lot of real analysis books, is a bit hard to understand, I think. But it actually relies on a simple lemma, which is not too hard to understand. So here's the statement of the theorem. Now let's prove a lemma. And this lemma is like the main fact that goes into the proof of the theorem. So the theorem is, the lemma is, suppose that we have a function from one metric space to another metric space. And suppose that for every epsilon greater than 0, there is some continuous function g from E to E prime, such that for all p in E, the distance between f of p and g of p is less than epsilon. Did I use the correct notation? Yes. Yes. Okay. Yes. I'm using the d prime for the metric on E prime. Okay. So we have some function f, and we're supposing that for every epsilon there's a continuous function g that's within epsilon of f, meaning that for all p and e, the distance between f of p and g of p is less than epsilon. Then the statement is, then f is continuous. So let's prove it. Well, first let's draw a picture just to illustrate what's going on. Right. So maybe I'll draw a picture kind of on the side, but then we have the main proof. So we want to show that f is continuous, and so what we do is we let p naught be an element of E, and then we let epsilon be greater than 0. So we want to show that there is a delta such that if p is an E and the distance between p and p naught is less than delta, then the distance between f of p and f of p naught is less than epsilon, right? So we have a p naught in E. Okay, so here's our E. Our E is R, and then our E prime is also R in this picture. Well, we have this function g, which is continuous. So we know that there is a delta. We know that there's a delta for this particular epsilon. We're given epsilon, and we know that there is a delta such that for all p in the delta ball of p naught, the distance between g of p and g of p naught is less than epsilon, right? So we have this function g. For simplicity, I'll just assume that g is just this straight line. Okay, so here's g. And then, so we're given epsilon. I should have drawn epsilon first. Well, here's g of p naught. Okay, here. and we're given this epsilon. And we know that there is a delta such that when you plug in all the values between within delta of p, you remain in this epsilon interval. Right? So now you have this f, right? G is continuous, and you have this function f, and you know that f is never too far away from G. So let's just put in a random point P here. Okay. Should I just draw a different picture? This might be too crowded. Let's say I have a P here. So I have this G of P naught, and then I have this G of P here. Yeah, this is a little too crowded. Okay, maybe I'll draw a different picture. So you have this, and then, okay, let's say that I have E here, and then this is P naught. So this is my G of P. P naught, and then I have this P, let's say it's out here, just so that I have more room. So now I have this G of P. Right? P is my arbitrary element within epsilon of P naught. So maybe this distance is delta, and that distance is delta. So I know the distance between G of P and G of P naught is less than, this distance is less than epsilon. Okay. Now I have this function f, and I know that since G approximates f, so I have this function f, G of P naught is within epsilon of f of P naught, and G of P is within epsilon of f of p. So if you have this picture, what's the farthest that f of p and f of p naught could be? So if your G of p is here, right? You have this p comma G of p here. Your f of p must be within epsilon of G of p. So your f of p, okay, if this is like the farthest down f of p could be is epsilon less than G of p. So the lowest your f of p could be is like here. That's less than epsilon away from G of p. And similarly, your f of p naught, so your G of p naught is up here, right? Your f of p naught, since G approximates f, that's the condition we're given. We're given this G such that for all p and e, the distance between f of p and G of p is less than epsilon. So we're applying that to this particular p here, and we're applying it to p naught. The distance between G of p naught and f of p naught must be less than epsilon. And so the farthest that, if this is where your G of P naught and f of P are, the farthest f of P naught could be away from P is if f of P naught is all the way up here. So this distance must be less than epsilon. So if you want to make your f of P and f of P naught as far as possible, you're going to have to make f of P naught all the way up here, but it's still not that far away. Right? So this distance is less than epsilon. This distance is less than epsilon. This distance is less than epsilon. So your f might be something like like that or something. And so in this picture, we see that the distance between f of p naught and f of p must be less than 3 epsilon. And that's for every epsilon, right? So for every epsilon, there exists delta such that for all p that's within the delta neighborhood of p naught, the distance between f of p naught and f of p is less than 3 epsilon, and we can modify the proof, we can modify the argument so that we get it less than epsilon, and that shows that f is continuous at p. So let's write down the formal proof, but this picture illustrates the idea. The proof of the lemma is, so where did we, okay, we have this part. P naught is an E, let epsilon be greater than 0. There's a delta such that for all P in the delta neighborhood of P naught, the distance between G of P and G of P naught is less than epsilon. And then in addition, we have that the distance between f of P and G of P is less than epsilon, and the distance between f of P naught and G of P naught is less than epsilon. And therefore, now we're able to get the bound by the triangle inequality. The distance between f of P and f of P naught is less than or equal to the distance between f of P and G of P plus the distance between G of P and G of P naught plus the distance between G of P naught and f of P naught. And each of these are bounded by epsilon, and so the sum is bounded, the sum of these three things is equal to 3 epsilon. And that's it. Actually, each of these things are less than epsilon, so the sum is less than 3 epsilon. And now we can use this general principle that we found that the distance is less than 3 epsilon, but we can modify the proof, right? We just take epsilon, everywhere we saw an epsilon in the proof, we replace it by epsilon over 3. So what do we need to do to modify this? There exists delta such that for all p in the delta neighborhood, the distance between G of P and G of P naught is less than epsilon over 3. In addition, we have the distance here is less than epsilon over 3, distance less than epsilon over 3, and now you just get less than epsilon. And that completes the proof that f is continuous. So this is how do we assess this proof? Once you draw the picture and get the idea, it's not so hard, right? The idea is that you're trying to show that f is continuous. You know that g is continuous, so you can bound the distance between, like, there's a delta such that for all p within delta of p naught, you can bound the distance between G of P naught and G of P. That's a really small number. And then since G approximates F, you get a bound on the other two distances you need. And then you use the triangle inequality. And then that shows that the distance between F of P and F of P naught is going to be less than epsilon. Okay? So intuitively, what this is saying, what this lemma is saying, is that if your function f can be approximated uniformly by a continuous function, so there's a continuous function that's less than epsilon away from f for all epsilon, then f must be continuous. And now, from this lemma, that's the main lemma that we need. It's actually not too hard to see that this theorem is true. So let's go back to the proof of the theorem, that if you have a sequence of continuous functions and the sequence converges uniformly to this function f, then f must be continuous. Actually, I would encourage you to try to come up with the proof yourself, because there's really only like 2 lines left. So the proof of the theorem Well, so we want to show that f is continuous, right? So let p naught be in E and let epsilon be greater than 0. We know that there exists, since the convergence is uniform, we know that there exists some integer, some positive integer n, such that for all little n greater than capital N, and for all p in E, the distance between f of p naught, for all p in E, the distance between f of p and fn of p is less than epsilon. Well, now let's just fix any n larger than capital N. Any little n will work. Say n equals capital N plus 1. And then we get this f sub n, and then we apply the lemma above with g equal to f sub n. Right? Your f sub n satisfies the property of this lemma. Right? Fn is continuous, and the distance for all p and E, the distance between fn of p and f of p is less than epsilon, and then this lemma says that f is continuous, and that's the theorem. So I hope that this video helps you make sense of the proof of this theorem. I think this picture, maybe not this first picture, but this second picture is helpful for understanding what's going on, and what I wanted to do was to isolate this lemma and then prove the theorem afterwards. I mean, this lemma somehow is the main, it's like a theorem on its own. It's the main result that we need. And then the theorem about the uniform convergence and the limit being continuous is really just a simple consequence of that lemma. Okay, thanks. Oh, and by the way, this kind of result is used when studying things like series, things like integrating power series or swapping the limits, limit operations with integration and differentiation and things like that. Okay, thanks.